All right, welcome back to the deep dive. Today we're diving into the world of cell membranes.
Ooh, cell membranes.
Yeah, specifically all the crazy ways scientists are figuring out how to control what goes in and out of cells, by messing with their membranes.
Sounds complicated.
Well, it is, but it's also super fascinating. And you, dear listener, want to get up to speed quickly. You don't have time to wade through tons of research papers. Luckily for you,
We've got you covered.
that's right. We've done the heavy lifting for you, combed through the latest research.
Chemical techniques, physical methods, even genetic engineering.
Yeah, all kinds of stuff. And we're going to break it down, make it crystal clear how scientists are actually manipulating these tiny but oh so important cell borders. So think of this deep dive as your shortcut to understanding this cutting-edge area.
Exactly, a shortcut. Let's get started. Maybe we can begin with the chemical methods.
Chemical methods, okay. So it seems like certain molecules can actually make a cell membrane, like more porous. Is that right?
Right. Think of detergents and surfactants, things like Triton X100. They're kind of like soap, with oily and watery parts.
Okay, so they're like slippery.
Well, yeah, in a way. So picture this. The cell membrane also has oily and watery regions. These detergents, they slide right in there, disrupting the membrane structure and making it leakier.
Makes sense, kind of like loosening up the border control.
Exactly. And this can be super useful, It lets scientists gently release valuable stuff that the cells are making, like enzymes or metabolites, without having to completely destroy the cells.
So it's a way to tap into those cellular factories without, like, breaking the machinery.
Precisely. It's a game changer for lots of industries. But of course, we have to be careful with these agents. Too much, and, well, they can harm the cell.
Right, like anything. Too much of a good thing.
Exactly. It all comes down to careful optimization.
Okay, so that's detergents and surfactants. What about those organic solvents I was reading about, like toluene and ethanol?
Organic solvents. Those work a bit differently. They mainly target the oily parts of the membrane, making the whole structure more fluid. Like, imagine a pat of butter getting soft at room temperature.
Gets all melty and permeable.
Yeah, exactly. And this increased fluidity, it makes it much easier for other oily substances to slip through the membrane.
Interesting. So if you need to pull out something that doesn't mix well with water, an organic solvent could be the way to go.
Right. But again, like with detergents, they can be a bit rough on the cells. Toxicity is always something to watch out for.
Right, and they can mess up the cell's machinery, the proteins.
Yeah, that's another important consideration. So yeah, you've got to be careful there too.
And then there are those chelating agents, like EDTA. It seemed like they had a more specific target.
You're absolutely right. EDTA is particularly good at targeting gram-negative bacteria.
Gram-negative bacteria, those are the ones with that extra tough outer layer.
Right. Yeah, exactly. They have an outer membrane that relies on metallic ions like calcium and magnesium for stability. And EDTA, well, it loves to bind to those ions.
So it basically weakens their defenses.
Precisely. It makes the outer membrane more permeable, which means that drugs, like antibiotics, can sneak in more easily.
Ah, clever.
Yeah, it's a bit like removing some bricks from a protective wall. But keep in mind, EDTA mainly affects that outer membrane, and if you use too much, well, it can still be harmful to the bacteria.
Okay, so that's the rundown on the chemical side of things. But what about those physical methods? I mean, using things like temperature to change membrane permeability, that's pretty wild.
Yeah, it's a bit mind-blowing, right? The thing to remember here is that cell membranes are actually very dynamic. They're constantly in motion.
Oh, so it's not like a solid wall then?
Nope, not at all. And because of this constant movement, sudden changes in temperature, whether it's getting hotter or colder, can actually jumble up the arrangement of those lipids in the membrane, creating temporary openings.
I guess that makes sense. Like shaking up a jar of marbles, suddenly there's more space between them.
Exactly. And these temporary openings, well, they allow things to pass through that normally couldn't. It's a technique that can be used for things like bacterial transformation.
Transformation, that's where you introduce DNA into bacteria.
Right. Or it can be used to release proteins that are located near the membrane. But the key here is that it's a transient effect. It doesn't last forever.
Okay, so it's more like a quick in and out kind of thing.
Right. And you have to be careful, too. Extreme temperatures can stress the cells, even damage them.
Right. So you can't just blast them with heat or freeze them solid.
Nope. It's all about finding that sweet spot.
Got it. Now, what about electroporation? That one sounds almost futuristic, using electricity to poke holes in cells.
It does have a bit of a sci-fi ring to it, but it's a really cool technique. Basically, you apply these very short, very high voltage pulses of electricity. And these pulses, They create temporary pores in the cell membrane. And because these pores are bigger than the normal gaps in the membrane, they allow larger molecules to pass through, like DNA or RNA, even proteins.
Wow, so things that normally wouldn't stand a chance of getting across the membrane can now slip right in.
Exactly. It's a technique that's being explored for all sorts of applications, from drug delivery to basic research.
Super versatile then. Are there any downsides?
Well, the pores are temporary, so you've got to work quickly. And you need specialized equipment to generate those high voltage pulses.
Okay, so it's powerful, but not exactly something you can do in your garage.
Pretty much, yeah. Now, sonication and freeze-thaw cycles, those were also mentioned in the research.
Right, but it seemed like those were less about subtly tweaking the membrane and more about just blowing the whole cell apart.
You got it. Sonication uses high-frequency sound waves.
It's like a super-powered ultrasound.
Yeah, kind of. And freeze-thaw cycles, well, you're basically rapidly freezing and thawing the cells over and over again. Both of these methods cause the cell membrane to completely rupture.
So it's not about controlled permeability. It's about releasing everything inside the cell.
Exactly. It's useful if you want to study all the cell's contents at once, but it's not a way to carefully adjust what goes in and out.
Okay, that makes sense. So let's move on to genetic modifications, which seem to be the most, well, permanent approach.
Definitely. This is where things get really interesting. With genetic modification, you're basically rewriting the cell's instruction manual, the genes that control how the cell membrane is built and maintained.
So you're not just tweaking the existing membrane, you're actually changing how the cell makes the membrane in the first place.
Exactly. And by making these changes at the genetic level, you create stable, heritable changes in membrane permeability.
Wow, so the changes are passed down to future generations of cells.
Yep. One way to do this is by modifying the genes that code for transporter proteins.
Transporter proteins, those are like the gatekeepers of the cell, right? They decide what gets in and what gets out.
Right. And by tweaking their genes, we can control what they transport. For example, we can make a cell produce more efflux pumps, which are basically like tiny pumps that push unwanted substances out of the cell.
Interesting. So it's a way to enhance a cell's natural detoxification process.
Exactly. Or we could do the opposite. We could knock out the genes for certain uptake transporters, the ones that bring stuff into the cell.
So if there's something harmful that you don't want the cell to absorb, you can just block the transporters that let it in.
Precisely. And scientists are even engineering entirely new transporters designed to transport very specific molecules.
Wow, that's incredible. It's like designing custom-made gatekeepers for the cell.
It is. It's really amazing. And it's not just about transporters. We can also modify the genes that control the basic building blocks of the membrane, the lipids.
Right, the fatty acids and stuff.
Yeah, yeah. For instance, by tweaking the genes responsible for fatty acid production, we can change the membrane's fluidity. Like, if you increase the proportion of unsaturated fatty acids, you can make the membrane more fluid, which can be helpful for cells living in cold environments.
Ah, so you can basically give the cells a winter coat.
Haha, in a way, yes. And it's not just about fluidity, we can also change the electrical charge of the membrane by modifying those phospholipid head groups we talked about earlier.
So you can fine-tune how the membrane interacts with its environment.
Right. And even tinkering with the production of sterols or hopanoids can affect the membrane's rigidity and permeability.
Okay, so you can control the membrane's fluidity, its charge, and even its overall structure. That's a lot of control.
It is. And finally, there's the super precise approach of directly engineering channels and pores into the membrane.
Channels and pores, those are like pre-built tunnels through the membrane, right?
Yeah, exactly. So with this approach, you can either introduce entirely new channels, maybe borrowing them from other organisms, or you can modify the cell's existing channels, tweaking their size, their selectivity, how fast things pass through.
So it's like custom designing the entrances and exits to the cell.
Pretty much. And what's great about genetic modification is that it allows for permanent, tailored solutions, unlike those chemical and physical methods we talked about, which are often temporary.
Right, so it's the difference between putting a Band-Aid on a problem and actually fixing the underlying issue.
Exactly. And of course, which technique you choose depends on what you're trying to achieve, the specific cell you're working with, and the molecule you're interested in.
Okay, so we've covered a lot of ground here, from simple chemical disruptors to high-tech genetic engineering. It's really amazing how many different ways scientists are figuring out how to manipulate this fundamental barrier of life, the cell membrane.
It is. It really speaks to our increasing ability to not just observe, but actually control these essential cellular processes.
And it makes you wonder what the future holds. We've talked about some of the exciting medical and industrial applications, but beyond those, what other unexpected uses might these permeability altering techniques have? What other doors might we be able to open in the years to come? That's something to ponder.
Definitely gives you a lot to think about.
Thanks for joining us on this deep dive. Until next time.
See you then.
Bye.
Bye.